Okay, let's get started. So far we have been talking about the security foundations, many crypto tools. We talked about symmetric encryption, use symmetric encryption to build a MAC. We talked about hash functions, how password hashing will be different from simple crypto hash. We talk about public key encryption, RSA, and the digital signature. So today we will keep talking about the problems of public key crypto system and how do we address those issues. Like all other systems, it's not perfect. We try to address some of the issues, but still there will be many other issues. We also will spend a little bit of time to talk about random number generators. So as we said that symmetric key encryption is really fast. That's why even if we have public key crypto systems, we want to use symmetric key crypto to encrypt large amount of data. We only use public key system to transfer the keys. So to do that, we just let's say one party can generate a symmetric key and use another party's public key to encrypt that message and send it to that party. And that party will use its own private key to decrypt that message, which is the symmetric key for their future communication. So this is a standard approach for most of our protocols, because this is secure and fast. However, this paradigm still have a problem is how, in this case, we have party A and party B. Party A will use party B's public key to encrypt the symmetric key. So how can party A be sure that he is using party B's public key, not someone else's public key? If A use someone else's public key, then B will not be able to decrypt that, but someone else will be able to decrypt that, right? So the fundamental question is, how do we solve the problem of key authenticity? And we're going to solve this problem use public key crypto system itself. So we use public key crypto system to solve the public key crypto system's problem. So let's say this is related to how do we distribute the public keys of everyone, where and how do we store them, how do we obtain someone's public key. When we obtain someone's public key, how can we trust it is really someone from where it is claimed? So the distribution of public key is easy, okay? Let's say you generate a pair of public and private keys. Then you just broadcast. You tell everyone, hey, this is my public key. That's easy. The distribution part is easy. Or you say, I put my public key in a public server that everyone can access. That's not a challenge. The challenge is those approaches do not really solve the problem of the key authenticity. When you broadcast, this is my public key, how can someone believe you? When you put your public key in a public server, how can someone believe this is really your public key, right? So the solution is we just use a certificate, something we call it public key certificate or digital certificate. What certificate is basically the public key itself and your identity and a signature on top of that. How do we generate the signature? We use the private key to sign that. So a certificate is a binding between an identity to a public key. That's it. The mathematical core of the certificate is that. Of course, you can add many different additional information on top of that, which we will talk about. But the mathematical core is just the public key itself, your identity, and a signature of the whole thing. So we can write it this way mathematically. First of all, we assume there is a third party we trust. So that will be the root of trust. Whatever that third party say, we believe that's true. And that third party, we call it a central authority, or CA, in the public key infrastructure. So that CA itself also has a lone public key. We call it the public key CA. We don't know his private key. No one knows. Only the CA itself knows its private key. So the CA's job is to produce certificates for everyone. Let's say Bob here wants to broadcast his public key. So what Bob will do is Bob will first generate his own public key and private key pair. The private key part, Bob will just save security locally. Do not share with anyone. The public key part, then Bob will use to, Bob will concatenate his public key with his identity, Bob, and send the whole thing to the CA, obviously through a secure channel. The CA's job here is to verify if that public key really belongs to Bob and Bob's identity. Then the CA will just generate a signature for the whole thing, which is the public key and the Bob's identity. So by using this approach, we create a binding between this public key and Bob's identity. This whole thing, we can call it a simplified version of certificate. Then now Bob can distribute his public key, it's public anyway, and the certificate, can broadcast it. So when everyone get this pair, what they will do is they verify if this certificate is valid. If the certificate is valid, how do they verify that? Which keys were used to validate that? Yes, so they will use CA's public key because this is signed by CA's private key. Okay, so everyone has CA's public key and they trust that key. Okay. So the question here is, how do you trust the CA's public key? So this then will be the same problem, right? So anyone else would be able to verify if this key is valid. So this is the technique we use in all our systems right now. So I give you one concrete example. So phishing websites are still a very serious problem. There are many phishing websites out there. Those websites, they look like legit websites like PayPal, Outlook, or Amazon, but they are hosted by cyber criminals. Their sole existence there was to steal your credentials, your passwords, your account information, your credit card information. So they look like the legit website, but they do not have the legit website's address. They do not have the legit website's URL, right? So everyone here is computer science students. So when you visit a website, you will compare what you look at and also compare the URL. But for ordinary users, they do not really know that. So many of them were fall victim to this kind of phishing attacks. So how do we solve this problem? We solve this problem by using something called HTTPS. HTTPS also will encrypt the messages between your browser and your website. But another thing it can do is to prove the website identity. So basically, the website, when you visit a website, the website needs to prove its own identity to your browser. And how to prove that? The website will use a public key certificate like what we just described. Then your browser will verify that certificate to say if this is a legit website. So the problem obviously here is everyone can just create a certificate and sign a certificate. So how do we eventually find the root of trust? So who is the CA in this case? So let's take 2 examples. Let's say first we go to UB's website. Let me make this larger. Doesn't work. So you can say here, when I visit UB's website, this is a legit UB website, and we have the buffalo.edu, and my Chrome browser has a lock here. If you click this, it tells you the collection is secure, which means HTTPS, TLS is used here. We don't care about other things here. If you click this, you will say there is a sentence, say certificate is valid. If you click this one, you can see more information about the certificate. This is a website certificate sent to your browser. Your browser verified that. That's why your browser shows this lock icon to say this is verified. If you check the detailed information here, let's say a general information here, maybe. So this certificate is issued to this URL, which means the certificate is bounded with this URL, and there are organization names, organization unit, and this certificate is issued by another organization called R3, or their name is Let's Encrypt. That's the organization's name. That's who signed the certificate of UB website. And we can also find the validity information of this website, of this certificate. When is this certificate issued? It's like a month ago. And when this certificate will expire. So after this expire, after April 18th, you visit the website, you probably get a new certificate. Then also there is a signature of the certificate. If you check detailed information, it will be more interesting here. If you check detailed information, you see there are 3 layers. We go to the bottom layer, which is 3w.buffalo.edu. And this is, if you click this, you get the certificate of buffalo.edu. And this certificate has what? Version number, serial numbers, and also certificate signature algorithm. So we are using PKCS version 1 and SHA-256 with RSA to sign the certificate. Then who signed this? We already saw that. It's R3, right? So R3 signed this, which is a company, organization. Their job is to sign certificate. So they signed our certificate. But the next question is, who signed R3 certificate? Why should we trust R3 signature? So if you check what the browser will do, is also, it will check Buffalo certificate, it is valid. Then check who signed Buffalo certificate, check their certificate to say if that is also valid. So if we check here, you can say, we can find R3 certificate. R3 certificate has the same thing, like a version number, what a signature it used to sign the certificate, the validity, peer, those information, and also many other informations, including the crypto algorithm. And also, there is also an issuer. So who signed the R3 certificate is another organization called the Internet Security Research Group, ISRG Root X1. That is the organization who signed R3 certificate. So the browser will retrieve that organization's certificate and also keep verifying. And this certificate, you can say here, that's the root of trust in my browser. Or that's the root of trust for UB's certificate. In this case, who is the issuer? There's no other issuer. This organization self signed this certificate. They create a public key, private key for itself, and use its private key to sign this. So this organization self-certified that I'm legit. And our browser believes that this this organization is legit. That's because if you click in Chrome, the differences will be different. Windows and Mac, maybe the root of trust, those root certificates are at the OS level. At the Chrome, I believe it's at the browser level. So if you go to browser, privacy, and the security, then go to, sorry about that. Let me get rid of this. We go to security, then manage certificates, then authorities. You can find my browser actually trust so many root CAs. For my browser, those are all root CAs. And if we search internet, no, I cannot search here. Where is it? Go to security. So it must be somewhere. Here. Say, the Internet Security Research Group. So that is a group whose certificate my browser already trusts. Then this is a group who signed RS3's certificate, and RS3 signed the UB certificate. So we have a trust chain there, and the browser will verify this chain and eventually conclude that this UB website, the certificate is legit. Okay. If we go to another website like CBS News, they may have their certificate may be signed by a different organization, and that organization's certificate is signed by someone else. You can see here, actually we'll also have just the 3 layers here. It could be multiple layers. So CBS News website, their certificate is signed by RSA, secure server, and RSA secure server certificate is signed by RSA CA. Okay, so they're both part of the company RSA. So that is how certificate works in real-world settings. So like we said, mathematically, the core of certificate is just a public key. Oh, I forgot to show you guys the public key. Let's go to any of the certificate here. Then, where is the public key? Here, subject public key. For example, let's use this one. This one is a certificate of CBS News. And the CBS News public key will be this. Okay, so this is a 2048 bits of for what is this? This is N. Remember in RSA, N is public, and we have a small prime number E, and the E is also public. So this is E, only 17 bits, and this is N, 2000 bits. And the browser and the server will use this public key to get a new symmetric key and encrypt the future communications. So the mathematical core of the certificate is just the public key, the identity, and the signature of the whole thing. But in practice, there are many other, we add a lot of other meta information there. For example, we have the name of the owner of the certificate, and it's from country level to organization level to make sure this will not be there will be no two identities will have the same names. There will be validity dates. So the certificate we use right now is called the X.509 certificates. That's the format we're using. Okay, so you can see that for this public key crypto system, we always need a trusted third party. For my browser, you see there are, 50 trusted third party. Their certificates are pre-installed in my browser. Many of you use Chrome, use other browsers. You never check those information, but it's there. You may be able to add new certificates, root certificates to your browser. Some browsers support that, some may not. So the signing party, they will sign and publish the certificate. They also revoke certificates and publish something we call a certification revocation list. So let's say one party, let's say UB website, they have their own private key. Let's say if their private key is disclosed, is compromised, then we should not use their private key and public key pair anymore, right? No one should use that anymore. Then they should generate a new key pair. Also, their certificate should not be used because the certificate was associated with the old compromised key. Then the CA need to announce that this certificate is not valid anymore. That is something in a certification revocation list. We already say that there are so many vendors who can sign certificate. You can also, like I said, you can sign your own certificate, but your browser may not trust that. Some other famous big vendors to sign this. VeriSign is a big one. RSA is also a big one. Okay. So we already say this part. Okay. So next we move to public key infrastructure. So public key infrastructure is basically the infrastructure to help us manage certificates, manage the public keys. So the core of this is just a certificate. A public key infrastructure, or PKI, is a system for managing trust in public keys through the use of certificate. This is the basis for many of our services we are using. You are using this every day, but you probably never notice this, which means this has been quite successful. Because the goal of many of our security systems is try to be user transparent. So users do not need to know they are being protected, but they are protected. Yeah, question? They should never issue a certificate like that. They should verify the identity of the website, verify the URL. So they should never bind that fake URL with the identity of UB. That's their job to verify that. So you can consider those verification to be offline, to be manual, and they will verify those information. Yeah. That's why we trust them. Right? Yeah. Otherwise, everyone can generate their own certificate. Yeah. So PKI's goal is to eliminate the need for users to share pre-computed symmetric keys and enable the use of public key crypto. Many components of the PKI, we already talked about how the certificates can be issued. So before a certificate is issued, the identity and the credential of the user must be verified. using crypto means, like what you were asking just now. So usually offline to verify the identity. Then secure procedure must be used to generate the public key and private key for the certificate's owner, or some cases, we generate our own public key and private key and give that to the CA, and the CA will sign that. Obviously, when a private key is compromised, its corresponding public key should not be used anymore. Also, which means the certificate should not be used anymore. That's why we have a certificate revocation mechanism. First of all, there is an expiration date for each certificate. So there is automatic expiration. But also, if it's stolen, it's compromised, then we have the CRL list to broadcast to the whole world that those keys are not trustworthy or trusted anymore. Also, the PKI has other components to backup keys, recover keys, update keys. It also provides time stamping service. So all the certificate should have a time because there is an expiration date and time. That's why timestamp is also important here. So on top of a PKI, we can do a lot of things, and we call those PKI-enabled services. First of all, we can use it for secure communication, like as long as right now you are using a browser, you are using HTTPS, no matter what protocols you are running there, you are using a PKI-enabled service. Most likely TLS, and at application level, we have different, also other applications using public key, like the PGP, which we will talk about later. Also the virtual private network, and IPsec, which we will talk in the network security part. Also, we can use this PKI system to do access control and authentication. This is another popular usage of PKI. So I assume everyone here uses GitHub or something equivalent, right? So when you push code to your GitHub repo, do you always type your password? You don't. So how does GitHub knows you are a legit user? You have the access to that repo. You can't push. How does it know? Yes. So you first register on GitHub. After you register on GitHub, you will go to the security settings, and you can add many SSH keys there. So what are SSH keys? Those are just the RSA public keys. So the website knows your public key. You didn't provide the website a certificate. You just directly give the website your public key. And that public key is associated with your identity. Then whenever you push something, pull something, what the website does is run a challenge response protocol. So a lot of authentication is based on something called a challenge response protocol. So that protocol basically is, let's say, Anis, tell the website, I am Anis, I want to be authenticated. Then the website will generate a random number and the random number is not really a secret. Just generate a random number and give that random number to Alice. And ask Alice to encrypt or sign this random number using Alice's private key. That's it. Only Alice will be able to sign this, right? Because only Alice has a private key. It is also Alice's job to keep her private key safe. Then Alice will encrypt this private key using that random number, which generate this. This is called a response. So the server, what the server gives to Alice is called a challenge. The server challenges Alice to encrypt this message using the private key. Then Alice will encrypt that, get a ciphertext, get a response, send it to the server. The server has Alice's public key, so the server can verify, decrypt that to say if this is really signed by Alice. If this is signed by Alice, then the server knows this is a valid authentication request. So going back to the GitHub example, so what you do is you first locally you create a key pair, and that key pair will have obviously two parts: a private part, a public part. The private part will store your local disk, and you don't really share that with anyone. The public key part, you just read the content, you just paste that to GitHub website, so GitHub knows that's your public key. So whenever, usually, at least on my Linux system, how it works is that private key will have a specific name and reside in a specific folder. So when I do a Git push, the Git program will try to read my private key and use that private key to encrypt that challenge and send the response back to the server. So that is how the authentication works. So we will actually spend several classes on authentication. We will talk about machine authentication, human authentication, and this is obviously one way to do human authentication and also machine authentication. So any questions on the authentication part? So the goose, yeah. Well, the server needs to verify if you have the permission to push to a repo, right? Or even pull to a repo. It could be a private repo. Whether you are who you claim you are. There's an authentication part. Yeah. Of course, if you are talking about just a public repo, I'm not talking about public repo. A public repo anyone can pull, then doesn't really matter. Yeah. Okay, a little bit more about certificate. We already say that the certificate format we're using is X.509. It has the following fields we already looked at, like a version, the format of the certificate itself, the serial number, the signature algorithm, who issued the certificate, when the certificate is valid, who do we issue the certificate to, what is the subject, the owner of the certificate is public key, and what is the public key algorithm for that public key. And there are some optional fields. Then the signature over the whole thing, and that is a certificate. So the certificate use another X.500 names for subjects. So the names have a hierarchical format. First we have country, C, then we have O, organization, OU, organization unit, and also CN, common name. For example, if I want to generate a certificate for myself, then I will say the country US, organization UB, something like that. So this will make sure that no two entities will have the same name there. So ensures that everyone has a unique global name. Those are just more examples. We just saw CBS and the UB certificate there. Certificates, like we said, we can register certificates. We need to generate the keys, distribute certificate, issue certificate. we can retrieve certificate from different places and validate a certificate. Also, if they are expired, we also compromised, we can check CRL. So for our browser, when we get the certificate from the website, what the browser does is to verify the integrity and the authenticity of the certificate by verifying the signature. If the issuer of that certificate is not a root CA, then we keep verifying the issuer's certificate until we find the root CA which we trust, which is, in my case, is preloaded in my Chrome. Also, you need to verify the certificate is not expired, and also contact the CRL to check the certificate is not revoked. So, obviously, how do we design this CRL? The CRL should have a list of all the serial numbers of all the certificates that have been revoked. Obviously, we don't have to maintain everything in send the whole thing to everyone every time. That's why something called a delta CRL also exists. So the delta CRL only contains the newly revoked certificate, basically the changes from the previous version of the CRL. So that's how important the certificates are. And for the trust models, we already talked about one trust model, which is a browser trust model. In the browser trust model, the browser has some built-in root of trust, CAs. However, there are other trust models. Let's say one of them is this hierarchical model. In this case, we only have one root CA. So obviously, most of the system right now, we're not using this. We don't really blindly trust only one root CA there. So the browser, we have multiple root CA, many root CA, and the root CA sign certificate for other signers, and eventually the users will get their certificate from other CAs. So this has a tree structure there. Another approach is a networked PKI model. So in this networked PKI model, we have multiple root CAs, and they have their own tree there. Okay, they have their own domain, and we want to use one CA to sign the certificate of other CA, or even the child in that tree structure of other CA. So we can build some mesh network like this. So the root CA do not necessarily sign the CA root 1 doesn't necessarily sign its own certificate. Instead, the CA root 2 will sign CA1's certificate. CA4 will sign CA2's or CA3's. So this create a trust network. But you can see that in the broader example, it's not the case. Our root certificate was signed by the Internet Security Society itself. It's self-signed. That's why we have the web browser model. Obviously, we use this model because it's most convenient. And it's not perfect, but it's most convenient. That's why we're still using it. In this model, the browser preload a set of independent root CAs. And those root CAs, their certificates are just self-signed. Another very interesting model is used for email. it's not really used in the email we are using. For example, you are using Gmail or you are using UB Outlook. They are not using PGP. But PGP is something, it's more like a point-to-point. And if you can use this, but this is not associated with the signature of the UB already. So let's say PGP is designed for email. And in this model, each user is her own CA. So the PGP certificate has an email address, a public key, and the signature on that pair. So the identity here is the email address. And we also have the public key part, then we sign that. So, but when we sign that, we use your own private key to sign this. You do not find another CA, a trusted third party to sign. You sign this by yourself. Let's say Alice, PGP certificate will look like the data here will just the Alice email address. The Alice will self-sign this. The data has the email and also has the public key part. Alice will self-sign this. So, like we said, a self-signed certificate is not necessarily trustworthy because anyone can sign this, right? However, PGP can, so other people can endorse your certificate. Let's say we have Alice, we have Bob, then Bob can also sign Alice, the email address, public key, and the Alice signature, the whole thing. Bob can sign it again. When Bob signs this, Bob actually endorses that I believe this is legit Alice certificate. And more interestingly, in PGP, people can actually specify how trustworthy they believe the certificate they are signing. So this is a P2P network. There is no trusted third party. Let's say if Bob wants to sign Alice's public key or sign Alice's certificate, then Bob will retrieve the copy of Alice's public key, personally verify this is Alice's identity, then endorse that. Endorse means sign that. Then send this certificate to, you can broadcast that, to send it to everyone. Send it to Alice. Alice can forward this to anyone and say, hey, Bob endorsed my public key. So Alice will keep a collection of certificates she obtained from many different friends. And this data structure is called Keyring. And this name Keyring has been used in many places. Even the Linux kernel credentials, they have this Keyring structure. They have served a very similar purpose. So in PGP, Alice is also able to declare how much she trusts the owner of the certificate. Obviously, the previous trust, we just that implies fully trust. But in PGP, it can be the signer can give a confidence level there, how quantify the trust of the certificate. Then everyone can put their certificate in some public places. Like in PGP, there are keyserver.pgp.com, pgp.mit.edu. That's where people put their own PGP there. And also, you probably see some security professors before they were on their own website. They will have their PGP available. And if you email them, you can use their public key to encrypt. Then technically only they will be able to decrypt. Obviously, this is on top of the original email. Your ciphertext will be translated to just hexadecimal, then send as text, but that's actually encrypted. Besides the 509 certificates, there are other different certificate formats, and also at the UB, you can request your certificate. UBIT can generate that for you and sign with UBIT's private key. So if you want to learn more, you can also visit this website. Okay, so that is a basic idea of public key crypto system and PKI. So PKI somehow is, we use it every day, but the strict hierarchical model that the word has only one root CA, that model obviously does not fly. We're not using something like that. So recently, especially with the blockchain, the advent of blockchain has been changing the landscape a lot. Has been changing the landscape a lot. Blockchain, smart contract have been providing a lot of similar guarantees that our PKI used to provide, and also provide some guarantees PKI couldn't provide. We will discuss those in the Bitcoin session module of the class. So any questions regarding public key crypto system and PKI before we move forward? Yeah. No, usually no. This has nothing to do with the email provider. You do this on top of that. Like Gmail, Outlook, maybe some versions they provided that built in with PGP, but now not many people are using it anymore. So actually, for email part, there are some new standard to replace this. Not really replace, because PGP was only used by a small group of people anyway. To add the authenticity to the email, there are several protocols. I don't recall their names. Yeah. Any other questions? Okay, we're almost done with crypto part. Next Monday, we will do the key management for symmetric key systems. Then we can finally move to system stuff. So the last another topic I want to discuss today is random numbers. Obviously, now you understand crypto keys are super important. They are secret. But how do you generate secret keys? Basically, you generate random numbers. And all the crypto algorithms, except the hash functions, they rely on those keys, and those are basically random numbers. The symmetric key is just a random number. And the public key, also we use a prime random number which are primes but large. Also the paddings, the challenge, they are not necessarily secret, but they still should be random numbers. So what do we expect from random numbers, or just the random bits? So they should be uniformly distributed, no obvious statistical information that you can guess the random numbers, and they should be, let's say the bits should be independent to each other to make it more random. So how do we, and where do we find those kind of randomness? So we believe true randomness we can gather from the physical world, the unpredictable physical world. We can gather some true randomness. Let's say if but they do not necessarily are true randomness, because let's say if you want to use someone's keystroke pattern to generate randomness, but everyone have their own typing behaviors. They have their own, there may be some inherent characteristics behind that. So the randomness they generate, still there are patterns, right? So researchers have been using like noise from mouse, microphone to generate random numbers, but they're not necessarily true randomness, but pretty close, okay? Also, true randomness is really hard to get. That's why in real world, we use something we call pseudo random number generator, the PRNG, pseudo random number. The true random number generator, some hardware will provide that. It basically sends the physical word and generates that. But if you can influence the physical word, what it generates do not necessarily is true randomness, right? So a pseudo random generator is an algorithm. It takes a short value, we call it a seed, and as input, and it produces a long string that statistically close to uniform distribution. For example, if we have a k-bit seed, a pseudo random generator, it should have the period, the frequency of it should at least be 2 to the power of k bits. So then we think those are good pseudo random number generators. Also, there are tools to test the randomness of the net random number. They can quantify how random this is. The problem of those algorithms is, first of all, they are all deterministic algorithms. So given a fixed seed, it will always generate the same random number, the random number string. So like the C library function, rand, and also srand, they generated random numbers based on seed you give. If you always give the same seed, it always generates the same random number. It's deterministic. It's just the period for that is very long. So for most cases, it's secure enough. And we can even use this one. If we trust its output, we can use even as a string cipher. Let me show you another random number generator. So the Linux kernel actually provides random number generators. And Linux has two devices. One is called the device random. Another one is device urandom, to provide you crypto secure random numbers. Those two are kind of different. The device random will block. It will generate a higher quality random numbers. So if it cannot get enough entropy, the randomness maybe come from network, from your key type. If it cannot get enough entropy, then it will just block there, do not generate more random number. However, the disadvantage of its throughput is not as big as sometimes you need. That's why they have another device, is the urandom device. This device will not block. It will always generate random numbers using crypto algorithm. However, the quality may be lower. So on my computer, actually, if let's say so on my computer here, we just do a cat device random. You can say it's keep generating random numbers, and I have a very powerful computer, so it's never block. But if you try this on our Docker image, it may block. I remember on one of the devices we used before, it actually blocked. But if you do urandom, it will never block. It will always generate you with random numbers. Of course, we do not have to say the ASCII of it. If we say the hex, that will be, yeah. So we do a hex dump. You can see those are the random numbers my Linux kernel is generating for me. So and there have been some research to analyze if those random number are really secure, because the random number I just showed you is used on your operating system for many, many different things. For TCP connections, there is a sequence number. That sequence number starts with a random number. It's not starting from 0. We will talk about this in the network security part. And also, you use this for keys. So there is a research back in 2006. They analyzed Linux version 2.6.10 and analyzed their random number generator, basically the output of device random and device urandom, and to check if they are really secure. And they find many different attacks to influence those numbers, and also find that they are not necessarily have a very short period there. So one way to generate pseudo random number is just use crypto function. You have a seed, then you use AES counter mode, then you can generate a string, right? So that string, because of the property of symmetric key crypto, the output should somehow uniform distributed. That's why you can use that as a random number, but obviously it's not necessarily a very fast approach. So because the security of our systems eventually rely on the randomness of those keys. Many vulnerabilities have been discussed in our Linux kernel, in our other systems, because the random number cannot generate high quality random numbers. For example, this one, 2006, 1833, they find that on NetBSD, the Intel random number generated driver will always generate the same random number. Okay, that's a huge mistake. It means your crypto system doesn't work because your key is always the same. Also, 2007, find out the Linux kernel doesn't properly state the pool when there is not enough entropy. Also, Debian-based OpenSSL also use random number generator that generates predictable numbers. So those are a huge mistake, which renders the whole crypto system useless. Okay, that's basically what I have for random numbers. Next week, we first talk about how do we do key management for symmetric key systems. Then we will move to authentication first. After that, we talk about operating system security, software security, network security. So finally, we're almost done with the crypto part. Questions? I believe there are, yeah. But when they are compromised, it will be the same thing as other signers are compromised. They update their public and private keys. Everything has to be replaced. Yeah, because whatever you sign is not trustworthy anymore. Yeah. Okay, see you guys next week.
I don't find my name on the list.